All right, let's get started. Yes, Taylor, thank you. Let's get started. Very pleased to have Dr. Timothy Carleton here with us today. He is a postdoc at University of Missouri, where he works with Eugene Guo. Probably said that wrong. And he was actually at my alma mater of University of California, Irvine, where he beat me by 1 day defending. I think we figured out. So he has seniority here. Hopefully you will enjoy his talk. He's in graduate school. He's studied internal and external factors affecting galaxy evolution, and that is what he's going to be talking about today with ultra-diffuse galaxies. So,
thanks, Ben. Yeah, so I'm going to title my talk the formation. Oh, sorry. I didn't know I wanted lights on. Get back. Thanks for coming to my talk here. I titled it The Formation and Evolution of Ultra-Diffuse Galaxies. This is the main thing that's been driving my research interest over the past couple of years. So this kind of covers a few broad topics. And so just to kind of go over the talk, first a little bit of background about these UDGs, what they are, why we care about them. Then I'll talk about a mechanism for the formation of UDGs through tidal stripping and heating of normal dwarf galaxies. That will kind of be the first part of the talk, and then I'll talk a little bit about the origin of globular cluster systems around these UDGs and what we can understand about those systems. And then, kind of to wrap it up, I'll kind of zoom out a little bit and put these UDGs in the context of our overall understanding of dwarf galaxy evolution. All right. So first, ultra-diffuse galaxies. These are the rare case in astronomy. It's exactly what it sounds like. These are just very unusually large dwarf galaxies. So to put it in the context here, I have the half-light radius of galaxies on the y-axis here, and the stellar mass on the x-axis, spanning a pretty broad range, about 10 orders of magnitude in stellar mass. These are all early type galaxies. You can see generally there's a pretty tight correlation between the stellar mass of the galaxy and its size, going all the way from these massive ellipticals down to dwarf ellipticals and the dwarf spheroidals of the local group. But around 10 to the 7, 10 to the 8, you have this kind of outlier population of galaxies that have low surface brightnesses and sizes over a kiloparsec and a half that kind of really stand out here. So we want to understand how this population is formed and what makes them different. And one other thing we've kind of known about these UDGs is that they're primarily identified in clusters. So the seminal UDG paper was back in 2015. Peter Van Dokkum et al. Found a pretty significant population of these in Coma, but even if we go back to the 80s when we just were first looking at low surface brightness galaxies in Virgo, they're primarily identified in clusters. And as we've kind of taken a holistic approach to them, looking for them in clusters and groups in the field, they do tend to preferentially be around these denser environments. Here, the kind of red dots are UDGs in Stripe 82 observations, and so it's kind of hard to see with this projector, but they're generally found kind of in these denser environments. And one of the most intriguing aspects of these UDGs is that there is hints that they live in unusual dark matter halos. So this comes from a couple different lines of evidence. First, if you just look at you use globular cluster abundances to measure, to kind of infer halo masses. this is kind of what you get. So for non-UDGs, there's this pretty tight correlation between stellar mass and halo mass inferred from globular cluster counts. But you have this one UDG here that's a pretty significant outlier with a high globular cluster abundance that may be from a higher dark matter mass. And as we kind of have more observations of UDGs, they are more systems that kind of represent that space. But also, as we've measured dynamics for a few of these UDG systems, they hint that there are outliers in that space as well. So here, this is halo mass inferred from dynamics, where we have versus stellar mass, where you have these non-UDG systems following this pretty tight correlation, matching up with what the green points from simulation give you, but then you have this significant outlier of a UDG. And then, but you can also go the other way. So here, again, this is kind of a similar plot where you have lots of non-UDGs following this general trend. And you have some UDGs with very high velocity dispersions, indicative of an overmassive dark matter halo. But then you have this DF2 here with a very low velocity dispersion, consistent with like no dark matter at all. And so this kind of is indicating these types of galaxies have really unusual dynamics, maybe hinting at some unusual dark matter halo properties. All right. So we want to understand what's going on here, and so one of the places we can look to understand these galaxies is the effect of environment, because we know that they're primarily originally found in these dense environments, and we know that kind of the intense environment of a cluster, for example, can have a pretty dramatic effect on these dwarf galaxies. And as we've taken a look, we do see that there's significant evidence that of environmental impact on these UDGs in particular. So for example, if you look at the surface brightnesses of UDGs identified in cluster regions versus those identified in the less dense regions in the field, the UDGs identified in clusters tend to be a little bit more faint in terms of their surface brightnesses compared with those identified in the field. And also, if you look at the abundances of UDGs versus the host mass that they live in, the abundance kind of increases with halo mass beyond what you'd expect if they were just kind of a constant fraction of the dwarf galaxy population. And the corollary of this is that there are actually more UDGs in clusters than in the field, and this turns out to be true, where you have about 3%, UDGs represent about 3% of the stellar mass in clusters, whereas UDGs in the field are about an order of magnitude less than that. And so there is some environmental impacts here, but if you look at the morphologies of UDGs, you see evidence that tidal interactions in particular played an important role in their evolution. So here, if you just look at the axis ratio distribution of UDGs, you can see that it's more consistent with a prolate kind of stretched football-like morphology than randomly oriented disks. So if UDGs were just like randomly oriented disks in clusters, you'd expect to see a lot more kind of face-on high axis ratio systems, but that's not the case. And so you really need this kind of stretched football-like morphology. And then really intriguingly, if you look at this is the distribution of orientations of UDGs. This is the angle between the major axis of the UDG and the cluster center. And it's not just kind of randomly dispersed throughout the cluster. You have preferentially many more things pointed towards the cluster center rather than away from the cluster center. And so I think this is pretty good evidence of tidal interactions. And then there's been at least 2 systems now that have been identified where there's a tidal stream connecting UDG system with a host or parent galaxy. So this, again, is some pretty significant evidence of tidal interactions. So kind of with all this environmental evidence, we can ask the question, can tidal interactions alone explain this UDG population? So that's going to be the question I'm going to address first, try and answer that. This is work I did as part of my thesis with Mike Cooper, Manoj Kaplikat at UCI, Raphael Irani and Jorge Rubia in Edinburgh, and a little bit with teaching at Missouri. All right, so to answer this question, we're going to turn to some results from high-resolution in-body simulations studying the effects of tides on galaxies in particular. And what these simulations show is that the effect that tides have on the dwarf galaxy can be parameterized remarkably well if you just look at the amount of dark matter mass lost due to tides. You can measure the change of stellar mass and the half-life radius just based on that variable. So that's good news for us because that's something we can kind of get from a simulation and see how the galaxy evolves following those tides. And another result from these simulations is that core dark matter halos result in significantly more expansion due to tidal heating than galaxies in cuspy. And so the way this works is if you have so a galaxy in a cuspy halo, so here the solid line, the black line is this dark matter, and the solid lines are and dashed line is kind of the before and after case. Galaxy in a cuspy halo loses its mass primarily in the outskirts because it has this strong central potential. And so the galaxy itself, which is kind of more concentrated, isn't as effective and doesn't have this significant tidal heating. Whereas the galaxy in a core dark matter halo, it doesn't have this as strong of a central potential. It's able to lose mass in this kind of central region, and the galaxy expands significantly throughout the course of its orbit. And so, kind of with the results from these simulations, we can build up a model and look at how an overall galaxy population would evolve as they experience these tidal effects in a cluster. And so that's what I'm going to do. I'm going to just go into the illustrious dark simulation and draw all the subhalos around these some of the massive clusters in the simulation, and kind of model this galaxy population. At infall, kind of give it an initial stellar mass and half-life radius from some empirical relationships, and then I'm going to derive the amount of mass that's lost due to tides from the orbit of the subhalo in the cluster. Crucially here, I'm not just getting the mass loss from the simulation because one, this is a dark matter only simulation, and so it doesn't have any core halos, but two, there's some recent results from Frank Vandenbosch et al. Saying that the mass loss measurements for these particularly stripped systems may be significantly off in body simulations, and so we want to avoid that systematic effect because we are looking at the most stripped systems in particular. And so we have the mass loss, and so we can use those tracks, tidal tracks, to get the final stellar mass and half-life radius of our galaxy population. And so this is the result that we get for one of our clusters that we model. So here, the blue line and the dashed regions are the initial size-mass relation for our galaxy population. And after we run through the model, all the systems end up as points here, where the points are color-coded by the amount of mass loss that they've experienced. And so we can compare that population with the UDG population here with the gray squares and points being observations. So for galaxies, if we modeled them in cuspy halos, they didn't experience as much mass loss, and when they experienced mass loss, they didn't experience so much expansion to end up in this kind of UDG region. So you get some UDGs here because you're still stripping stellar mass, and you even get some UDGs based on just kind of scatter and the initial size-mass relationship. But you don't get a UDG population that really kind of fills up the box in the same way that we see the observations. But when we modeled galaxies in core dark matter halos, we got significantly more mass loss and corresponding expansion, so that we do get a pretty significant UDG population here. And kind of if we look at this population in a little bit more detail, this bears out. So here, this is both the stellar mass distribution and half-life radius distribution of our UDGs compared with observations. So here, the teal is our UDGs in core dark matter halos, purple is those in cuspy halos, and then black and red is what we're comparing to, the observations we're comparing to. So if we look at the mass distribution, both core and cusp case match up pretty well. This is mainly just an effect of where we decide to draw the box of what is a UDG and what isn't. But when we're looking at the size distribution of UDGs, in particular, the fact that the core model reproduces the size distribution remarkably well, I think is a pretty good evidence that this mechanism is a primary driver for UDG formation. We're getting not only just this population of larger UDGs, but the right proportion of smaller UDGs to large UDGs. And I think that's a pretty unique way we're able to get these UDGs.
Can you go back to your previous figure?
Yeah.
So you said the core stuff doesn't come from a simulation, right? So you said you modeled it.
Yes.
So what did that entail?
So I, for each dark matter halo, I go in the simulation, I get this mass, and then I get the concentration from the mass concentration relation, and the scale radius corresponds to the core size.
Okay, so basically just like replacing the subhalos
Yes.
with something.
With the core subhalo. So I only use the infall mass of the subhalo and its orbit throughout the cluster.
Okay. And it's constrained by the concentration mass relation in the core.
Yes. So we get these corresponding smaller and larger size UDGs that's kind of match observations. All right, and so we have this model. We can make some predictions from this model, something we can test. So one unique prediction of this model is that UDGs should be really old galaxies. In particular, the largest UDGs at 3 kiloparsecs or bigger should be just uniformly old, because the only way to get these large systems is to have multiple drastic orbits that they're going to lose a lot of their stellar mass, a lot of their dark matter mass. Whereas kind of smaller UDGs, you can either get, you don't need this 99% mass loss, you can get just with a couple of orbits, a couple of dramatic orbits, or maybe fewer, less elliptical orbits. And so we would expect this kind of L-shaped relationship between the age of the UDG and its size. Additionally, we can make a prediction for the velocity dispersions of these UDGs. Remember, I just used typical abundance matching to populate this my galaxies, so we expect these UDGs do live in dwarf-scale dark matter halos, so I'd expect dwarf-scale velocity dispersions. And that's kind of what you see here. So the contours are the representative galaxy population, and the points here are the UDGs with the interquartile range, with the velocity dispersion versus stellar mass and size. And so, again, because there is some significant stripping, the UDGs have slightly lower velocity dispersions than average, but it's not a dramatic effect. And so this naturally reproduces systems like this is DF2 with a low velocity dispersion, because you're getting rid of a lot of the dark matter, and so you get a low velocity dispersion. But it does have a kind of a difficult time reproducing those larger velocity dispersions. So kind of come back to those in a little bit. We'll see if we can figure out what's going on there. All right, so for this model for UDGs, the main takeaway here is UDGs are dwarf galaxies that have experienced significant dispersion. They should have these small velocity dispersions. They should kind of follow the mass-metallicity relationship because they have kind of similar star formation histories of other dwarf galaxies before they were grouped off the cluster. And primarily, they should live in these core dark matter halos. Then we have this prediction that large UDGs have uniformly old stellar populations, and there's a significant environmental and redshift dependence to UDG abundance because higher redshift clusters, you wouldn't have as much time to experience these tidal events. All right, so as we put this model out there, and since then there have been some more observations, let's see how this model does. So as we've looked at further dynamical and structural evidence in particular, this model seems to do pretty well. As we've gotten more velocity dispersion measurements, we see that a lot of UDGs have these more dwarf scale velocity dispersions, so that some of the earlier systems that have been really off the charts may have been just some outliers in some unusual cases. And so that kind of matches up with our model. We look at one system where we have this velocity dispersion profile measured with the cosmic wave integer. It's consistent with living in a core dark matter halo, which again is kind of an important component to our model. And then if we look at the axis ratios of UDGs, we see that they have a correlation with environment as well. And so this is kind of, again, pointing to this environmental dependence to UDG properties. Yeah?
Is the one that they have the profile for, is it also consistent with the custom profile?
So it's also consistent with the custom profile if you give it a pretty significant MSR. But it's definitely consistent with the code. All right. But as we've got some more stellar population evidence, this is kind of more of a mixed bag. So first, if we're looking at the mass-metallicity relationship between for these UDGs, this matches up with our prediction because they're generally lying along the mass-metallicity relationship for other dwarf galaxies. But if we're looking at the ages of these systems, it doesn't quite match up with what we're expecting. So here, kind of want to focus on the teal points. And this is kind of the same size age plot that I was showing earlier, and there's not really as much of a correlation as we'd expect. There's still not a whole lot of data points here, but it is kind of to the point where it is kind of providing some tension with the model. And then if we look at the phase space that these UDGs live in nearby clusters, it's not really consistent with these being primarily really early infall systems. So this is just kind of phase space with later infalls being to the right and earlier infalls being to the left. And we see a lot of these UDGs, the blue points are UDGs here, a lot of these UDGs are later infall systems compared with being earlier infall systems. So there is kind of some tension here with what we're expecting. And then there's the globular cluster systems. So one of the really intriguing observations of UDGs is that they have this significant globular cluster population. And on average, kind of the number to keep in mind is that UDGs have about 5 times more globular clusters than non-UDGs at a given stellar mass. Here you can see there's a lot of scatter in this relationship, but it is statistically significant. So this is some kind of component of the model we want to understand, and there's nothing that I talked about so far that could address this globular cluster population. Everything is, I didn't mention anything about globular cluster formation, and the only thing kind of could be is if it's related to the dark matter halos. And so this is kind of bringing me to the next part of my talk, where I'm looking specifically at the globular clusters around UDGs. This is work I'm doing with Yijing, as well as Farah Munshi up in Oklahoma, and Michael Schmill and Anna Rice at Yale. So what's going on with these globular clusters? So to address this question, we can kind of go back to the same procedure we did in the first part of the talk. We look at the effective environment, because cluster environment has such a significant impact on these dwarf galaxies. And it turns out that this is something that's been observed before, where globular cluster abundance does seem to be dependent on environment even for non-UDGs. So here, this is the specific frequency of globular clusters. This is just the abundance of globular clusters per unit luminosity normalized the Milky Way. So kind of more globular clusters, higher numbers there. And back all the way in 2008, it was observed that slightly more massive dwarf galaxies in Virgo show this relationship where systems close to the center have more globular clusters than systems further in the outskirts of Virgo. And it turns out that this is something that's present among the UDG population as well, where UDGs close to the cluster center have more globular clusters than UDGs in the outskirts. So here I'm going to really do my best to make sure I'm saying globular cluster versus galaxy clusters. We've got all the clusters going on here. And so this environmental dependence indicates that this might not be a primordial, that globular clusters isn't something necessarily set primordially for these dwarf galaxies. And it turns out this kind of effect has been looked at before. This is from Mastani et al. 2016, where they had a model for globular cluster formation that's kind of more continuous throughout time, rather than just kind of being set at like redshift 5 or whatever. And they were able to get this kind of environmental dependence where, so here this is similar globular cluster frequency versus stellar mass. For field galaxies, you get fewer globular clusters. For systems in the outskirts of the galaxy cluster, you get slightly more. And for systems in inner region, you get kind of significantly more globular clusters than out in the field. And so this is actually a pretty simple model to see how it works. Let's kind of go through it here. So the main component of this model is observations that show that the fraction of stars that are formed in clusters, bound clusters, is proportional to the star formation rate surface density. And so this is based on some observations in the Milky Way and nearby galaxies, and it kind of fits into our intuition of star and cluster formation. If you have a region of very dense and intense star formation, you'd expect more of those stars to be bound together in a cluster than if, for example, something going on in the disk. And this has an interesting implication, though, for systems, for dwarf galaxies that go into clusters. So we can consider two dwarf galaxies that end up at the same stellar mass in a cluster. One that fell in really early and just was quenched, and then one that fell in later in time and got to the same stellar mass but was quenched later. Because this system formed more of its stars at early time, it had to form them at a higher rate. And so a higher fraction of those stars would be bound up in clusters. And so you would end up with that earlier infalling system having a higher globular cluster abundance for its stellar mass compared with the later infalling system. And this actually plays into our understanding of UDGs really well, because I've just been telling you that UDGs are preferentially these early infalling systems. And so we could see how they would be forming more of their stars in clusters compared with non-UDGs. And so to kind of look at this in a little bit more detail, we can again build up this model where I use that same tidal model to create a UDG population and model this cluster formation efficiency based on the star formation rate of the galaxy. So here I'm going into the illustrious T and G simulation, so I have that star formation rate information. And then I'm going to produce a realistic-ish globular cluster population where I'm not only just going to create these globular clusters, but I'm also going to destroy them through tidal interactions with their host galaxy and both the tidal interactions and interactions with the gas in the disk of the galaxy. Because if I don't do this step, I way overproduce the globular cluster abundances for every type of galaxy, and that's not realistic. But once I do that, I'm able to kind of compare that population with the redshift 0 population of these UDGs and other dwarf galaxies. And so if I kind of do that procedure, this is kind of the result that we get. So here, on the x-axis, I have infall time for a modeled galaxy, and on the y-axis, this is the overabundance of globular clusters. So it's just globular cluster mass relative to the average globular cluster mass for systems of that same stellar mass. And so early infalling systems, because they have this intense star formation, form many more of their stars in clusters than systems with a later infalling time. And so kind of highlighted blue systems are just non-UDGs and orange systems are UDGs. And so you see that everything kind of follows the same relationship. It's just that the UDGs have preferentially these earlier infalling times when the globular cluster formation was more efficient. And it turns out this is good for some other aspects of some other observational facts of UDGs as well. So for example, this is globular cluster mass versus cluster-centric distance. The black points here are the observed trend between globular cluster mass and distance for UDGs that's observed. And the blue and orange lines are the binned globular cluster masses for my model systems for UDGs and non-UDGs respectively. Again, UDGs and non-UDGs have this kind of similar formation, but because UDGs were earlier infalling systems and preferentially migrate towards the cluster center, you get this trend with cluster-centric distance. And again, here if we'll kind of look at the globular cluster fraction versus size, this is an interesting observation where the larger UDGs have more globular clusters, and kind of some people have pointed this as evidence that globular clusters are kind of formation is producing the feedback that puffs these galaxies up, but this correlation is naturally reproduced through this model where earlier infalling systems that are kind of puffed up due to tides more preferentially have these higher globular cluster fractions. And so that, again, this model kind of reproduces that observation pretty well. And so we have that all. We can kind of look at some prediction here, and again, we have this prediction that the systems with the most, kind of with the oldest cell population should have the largest globular cluster fraction. Again, regardless of whether you're a UDG or not, there should be this correlation between galaxy color or age and globular cluster fraction. So that's something.
Why is that not metallicity? How can you interpret G minus R just as age in this case?
So it is, metallicity does play a role here, but so this G minus R color is directly from the simulation, and so it has both those age and metallicity components going in there. And so the effect of metallicity is slightly normalized out because we're normalizing the x-axis by cell mass, and so that does kind of get rid of some of that. All right, and so when we're looking at these globular clusters, and for this model, we get that UDGs have about 3 times more globular clusters than non-UDGs at a given mass. And that kind of really the main variable we want to look at is infall time. Systems with earlier infall time have more globular clusters than systems with later infall time, and that there should be a significant environmental dependence to UDG abundance and properties. So that's something we can look for in the future. So kind of in conclusion for this first couple parts of the talk, the tidal effects and environment play a particularly important role in UDG evolution. But this can't be the full picture because there were kind of a few parts during my talk. You might have noticed that I was like, well, this doesn't quite match the observations, these velocity dispersions, the stellar populations of UDGs, maybe some of the complete abundances of globular clusters didn't quite match observations. So this can be the full picture. So yeah, there's significant evidence of young UDGs, and not to mention the fact that there are these isolated UDGs that are not in any type of cluster environment, but still have these large sizes like these UDGs, and we don't have any way of addressing these populations at all. And so the way to kind of address that is to kind of revisit this starting size mass relationship. So for our model, all systems kind of started off on this dwarf-elliptical size mass relationship, but that might not be the case. A lot of systems may, for example, start off on a lower surface brightness disk star-forming size mass relationship. And this is kind of something that was examined in Solid in 2019. They had a mix of populations, and they got some velocity dispersions that matched better. So that's something we can kind of look at in terms of our model. For example, if we just adopt the star-forming size-mass relationship from the Gamma survey, we're able to get a lot of these UDGs, a lot of large UDGs. And we don't need as much stripping to produce a UDG in this case, because you're starting off a little bit kind of larger in general. And so because we don't need as much stripping, we're able to get kind of slightly higher velocity dispersions that start to get to a little bit of better agreement with some of the observations. And with that case, we're also don't get as strong of a correlation between the age and size of a UDG because, again, you don't need as much stripping to produce a UDG. But then we run into a problem if we just do this. This is the too many UDGs problem, where, so here the brown histogram is the size distribution of dwarf galaxies around 10 to the 8 in the 4-X cluster. So this is kind of just looking at UDGs. We see it, just dwarf galaxies. We see that there are a couple of UDGs here, but most systems are around a kiloparsec. If we adopt this kind of star-forming initial size mass relationship, whether you're in a core or a custom halo, things kind of, you get a lot of UDGs of 2 to 3 kiloparsecs or greater, kind of much bigger than the observed size distribution. It turns out this isn't something you, even if we don't adopt any kind of tidal effects at all, the distribution doesn't match what we see. So here, the black and whites are the, again, size and mass of systems in the 4-X cluster, and we just have this star-forming size mass relation with no stripping. We get this wide distribution of galaxy sizes, whereas we're really only observing systems around the kiloparsec. It turns out this is not something you can solve by adding redshift evolution into your size-mass relationship. So here, kind of the red and blue lines are the dwarf-elliptical and star-forming size-mass relations we adopt. And the lines with error bars are the size-mass relation for galaxies in candles at like redshift 0.3 all the way out to redshift 1.5. And so there's some, for star-forming systems, there's some evolution in the size-mass relation where things at higher redshift are smaller. But it's not nearly enough to resolve this discrepancy as a key number to think about. So we observe that roughly 20% of dwarf galaxies in clusters have these large, over 1.5 kiloparsec sizes. But if you go all the way out to redshift 1, where you'd expect most systems to have fallen in between now and redshift 1, it turns out that half of these similar mass systems have these large sizes. And so this redshift evolution isn't enough to explain the smaller sizes of the dwarf-ellipticals that we observe. And so we're left with this issue of what's going to cause this kind of smaller sizes of dwarf-ellipticals compared with the larger sizes of galaxies, dwarf-irregular galaxies in the field. So there has to be some other process that's going to shrink the galaxy sizes from these large systems to these smaller systems. And so I don't have another 10 slides where I'm going to solve this problem. I'm just kind of leaving this out in the open here. So there's some problem we need to address and look at further to try and solve. So environment plays a critical role, but it's not the full picture. So thank you all. Thank you.